Hi, everybody. Welcome back to another exciting episode of electricity. So we're going to do a couple of series circuit examples in this session. All right, I just have a few circuits and then we'll leave it at that. So we have a basic series circuit here, source of 20 volts, R1, R2, and R3, 200, 330, and 470 ohms respectively. So let's find IT and let's find the voltage at each resistor. Okay, we're going to do this the Ohm's law way, and we're going to do this the voltage divider rule method. All right, so just to do Ohm's law, let's find RT first, and we know RT is equal to R1 plus R2 plus R3, which is 200 plus 330 plus 470. Okay, and that equals 1K. Alrighty? That equals 1 kilo. So now, IT, we want to find the total current. We know that's E over RT, total voltage over total resistance, which is 20 volts over 1K. And that gives us 20 milliamps. So we know now that current in this circuit, IT, is 20 milliamps. All right? Now, to find the voltage at each resistor, we will take, so to find VR1, we'll do IT times R1, because we know IT is also the current through R1, through R2, and through R3. So VR1 equals IT times R1, which is equal to 20 milliamps times 200 ohms. And that will give us a grand total of 4 volts. So we would take 20 milli times 200 ohms, and that gives us 4 volts, okay? So let's just get in the habit of just marking on our circuit as we go along. This circuit is a story that should make sense at the end of it all. VR2 would be IT times R2, which is 20 milli times 330, and that gives us a voltage of 20 milli times 330. So we have 6.6 volts. All right. And then we have VR3, which is IT times R3. And that gives us 20 milli times 470 ohms, okay? Which is 20 milli times 470 is 9.4 volts. Okay? Now, we can also use Kirchhoff's voltage law to say that since E minus VR1 minus VR2 minus VR3 is equal to 0, we could say that VR3 is equal to E minus VR1 minus VR2, which makes sense, right? If we know the sum of the 3 resistor voltages is equal to E, then we'll know that this voltage across R3 would be E minus VR1 minus VR2, okay? Which would be 20 minus 4 minus 6.6, okay? Which gives us 9.4. All right? So just another way of doing it. So let's do this using the voltage divider rule method. voltage divider rule. So we know that VR1 is equal to R1 over RT times E, which is 200 over 1K times 20. And that would be equal to, well, 200 over 1K is 1/5, and 1/5 of 20 is 4. Okay, so VR2 is equal to R2 over RT times E, which is 330 over 1K times 20. And that is equal to, if we get it on here, 330 divided by 1,000 times 20, and we get 6.6. So we know it's going to work out the same, but because I'm a teacher, I'm going to go through it anyway. R3 over RT for VR3 times E, which is 470 over 1K times 20, and that will equal, nobody spoil this now, 9.4. Okay. Now, when we go forward, we're going to keep doing series circuits for a little bit. But you need to know that you need to understand how the voltage divider rule works and how Kirchhoff's voltage law works. Because when we get into series parallel circuits, or you get into more complicated systems, you need to apply those rules along with a few other rules we're going to learn along the way. Okay, so that's one example. Now this is a simple example where I gave you E and I gave you 3 resistances. Those are always easy. Okay, what if I give you this? So now I gave you E, I gave you VR1, I gave you VR2, and I gave you R3. So I didn't give you the all 3 resistances to make it easy. We did this. So you need to do some backwards calculations here. All right. So what we need to do is you need to stay organized. So I would consider this work, if I do say so myself, I would consider this work to be organized. Okay. I have all my variables. I know where everything is, and I'm following along in a pattern. So to stay organized, when we give you problems you need to work backwards, sometimes I make a chart, okay? Sometimes I make a chart. And it looks like that. And then R1, R2, R3, and total, okay? So I'm going to make this chart like this. I'm going to start the rumor that I invented this chart, okay? You're watching this video on the internet, which gives you a perfect forum for spreading that rumor. So you go right ahead. Okay, so I have this chart, voltage, current, resistance, and all my components. So what I'm going to do is I'm going to plug in the values that I gave you. I gave you E, so total voltage, 15 volts. I gave you VR1, which is 2 volts. I gave you VR2, which is 3.6 volts. And I gave you R3, which is 400 ohms. Okay, so your goal when you have this chart, and when we get into power, we're going to add a P column. Your goal when you have this chart is you want to have 2 values in the same row. Okay, you want to find a way to get 2 values in the same row. And once you do that, the chart will just fall together. So we don't have any rows with 2 values, but we do have this column that we can easily fill VR3. Okay, so we could say that VR3, using Kirchhoff's voltage law, we could say that VR3 is equal to E minus VR1 minus VR2. Okay, which gives us 15 minus 2 minus 3.6. All right. And that gives us, if you want to go at this, it'll give us 9.4. 15 minus 2 minus 3.6. Okay, so we get 9.4. All right. So let's plug 9.4 into that row. Okay, so these are the values I gave you. I gave you this. I gave you that. I gave you this. And I gave you that. All right, so now we have a row that has two columns, that has two values in that row, R3. So we know VR3 and we know R3. So using Ohm's law, we can find IR3. We can find the current in that resistor by doing IR3 is equal to VR3 over R3. Now this is where subscript notation is important to stay organized. We make sure we're using the right voltage and the right resistance. So we get here 9.4 volts over 400 ohms. So our current is 9.4 divided by 400, 23.5 milliamps. That is our current. So let's plug that in here. 23.5 milliamps. Okay. Now, if you remember, the current in a series circuit is constant, meaning that if the current in R3 is 23.5 milliamps, that means the current through the entire circuit is 23.5 milliamps. So we're going to say that IR3 is equal to IT is equal to IR1 is equal to IR2. Okay, so let's plug those values in our chart. There we go. Okay. And let's plug our values into our circuit just to stay organized. Nice. So we can easily find the other values. Okay. So to find R1, if I is equal to V over R, then R is equal to V over I. So R1 is equal to VR1 over IT, which is 2 volts over 23.5 milli. And that equals, if we go here, 2 divided by 23.5 milli, and we get 85.106 ohms. You know I like 3 decimal places. Okay, so R2 is equal to VR2 over IT, which is 3.6 volts over 23.5 milli, which gives us 3.6 divided by 23.5 milli. And we get 153.191 ohms. So we have that there. Voila. And then let's find RT. Now we have 2 ways to find RT. We have 2 ways to find RT. We could say that RT is equal to E over IT using Ohm's law. And we can also say that RT is equal to R1 plus R2 plus R3. So in both cases, we have 15 ohms, 15 volts over 23.5 milli, which gives us 15 divided by 23.5 milli. We have 638.298 ohms. okay? And we can also add them together. So if we add 85.106 plus 153.191 plus 400, 638.297. Now, we're off by 1/1000th here, okay? It's not a big deal. We're not calibrating my life support machine when I'm 90, so we're okay there. But there's going to come times where you think that rounding is okay, but that rounding follows through on other calculations, and you start getting some bigger discrepancies. Okay, so staying at 3 decimal places, if it's available, helps us stay as accurate as we can without bogging down our work, going to, infinite decimal places like pi. Okay, so that's what we have here. Just a second example. Now, let's take this circuit here. Let's take this circuit, okay? We have 4 resistors that are all 50 ohms. And we have a 20 volt source. So E is equal to 20. And then R1 is equal to R2, is equal to R3, is equal to R4, equal to 50 ohms. Okay? So we know through the voltage divider rule, RT here is 200 ohms. Okay? We don't need a calculator for that. We know through the voltage divider rule, 50 over 200 times E, 50 over 200 times E. So we know that VR1 is equal to VR2, equal to VR3, and is equal to VR4. Okay, which is equal to, you're going to divide this voltage by 4. So it's going to be 5 volts at each resistor. Okay, 50 over 200 times 20. So that is relatively clear. Okay. So my question to you is, what happens if we add R5 equal to 50 ohms? So what happens to this circuit now? R5 is equal to 50 ohms. So we know that the resistance in a series circuit is the sum of all the resistances. So now we know that RT went up. RT went up. So according to Ohm's law, if RT went up, then IT went down. Okay? Now we have 5 50 ohm resistors sharing that 20 volts, no longer 4. So what happened to VR1, VR2, VR3, and VR4? Right? So now we have a higher RT. So now VR1 is going to be 50 over, instead of being 50 over 200, it's going to be 50 over a greater number, which means that it's going to have less voltage. So VR1, VR2, VR3, and VR4 all went down. Okay, so if we prove that, RT is equal to 250 ohms now. So IT is now 20 over 250. Which is now 80 milliamps. Over here, IT was 100 milliamps, right? Because it was 200 over, it was 20 over 200. So IT went down to 80 milliamps. And now VR1 is R1 over RT times E. R1 stays the same. E stays the same, RT went up. So now instead of VR1 being 5 volts, now VR1 is going to be 4 volts. Okay, so that's what happens if we add an R5. So my next question is, what happens if we remove R3? What happens now? Well, RT now is equal to R1 plus R2 plus R4, which is 150 ohms. Okay, so RT went down. So according to Ohm's law, IT went up. Okay, so if IT went up and VR2 is equal to IT times R2, well then VR2 must have gone up. And VR1 and VR4. Those would have all gone up. So let's prove it. RT equals 150. So now IT is equal to E over RT equal to 20 over 150, which is 20 divided by 150, 133.333 milliamps. All right. And then VR1 is now equal to R1 over RT times E, right? R1 stayed the same, E stayed the same, RT went down. If the denominator goes down, then the result goes up. So we have 50 over 150 times 20. 50 divided by 150 times 20. And now we have 6.667 volts. Okay. Now we have 6.667 volts. So that's what happens when we add or remove loads from a series circuit. So I hope this helped. Stay tuned for more examples, and thanks for watching.